Okay, our next speaker is also a very good friend of us, Vladimir Kravchenko. We also met him in Rostov in 2021, in several times in Armenia, and we are extremely happy to have him here together with Alexei and the rest of the colleagues from the author network. So in particular, I am deeply thankful for you for having come here and join us in this conference. Okay, so our friend Vladislav, he's going to speak about serious representations for solutions and reconstruction techniques in inverse coefficient problems.
Thank you very much, Paco. Many thanks to the organizers for this opportunity to present my recent work to this great audience. This work will consist of mainly of two parts. So first of all, we will discuss this simple question: how to solve linear second-order differential equations with variable coefficients. And I will show you the way to construct so-called Neumann series of Bessel functions, which give a very attractive form of writing a solution of general linear second-order equation. Next, we will consider a very general inverse coefficient problem. I will explain why is it so general. Then we will see how we can solve this general inverse coefficient problem using the Neumann series of Bessel functions, with some numerical illustration to convince you that it really works. And some words in the end about inverse problems on quantum graphs, just some words. So this is the plan. And I will talk mainly about the Schrödinger equation here. So Q of x will be quite general from L1 space. L here, this L is finite, so we will consider in this talk only problems on a finite interval. Q, and it is important, Q here in general is complex valued. So of course, many results here are applicable in a much more general case because there exists such a nice Liouville transformation which allows us to transform a more general second-order equation into the Schrödinger form. So first of all, I will need just a couple of notations. We will denote two solutions of this Schrödinger equation as C of rho x and S of rho x. They will satisfy these initial conditions at the origin. So we write here this rho to make it clear that they are, for example, when I fix x, I can consider them as functions of the spectral parameter rho. It's very convenient. So C satisfies the same initial conditions at the cosine, and S satisfies these conditions, so it's 0 at 0, and its derivative is 1. Now, just to remind you that any series of this type, so some coefficients by the Bessel functions where this nu is fixed, and we are changing this n from, let's say, from 0 to infinity. Such series, they are called Neumann series of Bessel functions. This is just a quotation from the Watson's treatise of 1922. And the first who considered this kind of series was Carl Gottfried Neumann, not von Neumann. It was in 1960-something. And later on, Gegenbauer made a lot to develop the theory of such series. So there are many papers and books dedicated to this kind of series. So they are quite known object in mathematical analysis, but in fact I will show to you that they arise very naturally in the theory of differential equations, which is quite surprising. And especially they are very convenient for inverse coefficient problems. So with the help of the Neumann series of Bessel functions, I will show to you that we obtain not just a representation for solutions C of rho x and S of rho x, but a representation which is uniformly convergent in any strip in the complex plane of the variable rho, of the spectral parameter rho, in any strip parallel to the real line. Okay? Why this property is that important? Because when you solve direct or inverse spectral, for example, problems, you need to work with small spectral parameter and very large spectral parameter. It's very convenient. So these representations give you, you just consider the truncated sum of such representations, and you obtain the fantastic property that this truncated sum approximates well not only your solution for small rho, okay, but also for very large rho. Okay, you obtain a very nice approximation. So you will see it in a couple of minutes. So first of all, how we arrive at such kind of representations. Everything begins with these so-called transmutation or transformation operators. This is an object which is very well known since the work of Soviet mathematician Povzner of 1948. He proved that for our solutions, C of rho x and S of rho x, there exist these two representations. So there exist continuous functions, C of xt and S of xt, the kernels of our integral operators, which work in the following way. So these representations are for any rho, for any complex rho. So here the important feature is that the kernel doesn't depend on rho. Okay, so you just, if you suppose you know the kernel somehow, C of xt, okay, then this is just a second kind Volterra integral operator, which is the best operator, best possible integral operator. Okay, you can imagine with a continuous kernel. What else you can wish, yeah? And the kernel doesn't depend on rho. So you solve everything for your Sturm-Liouville equation, for example, okay, using this kind of operators. The problem is that nobody knows how to construct these kernels, okay? But they exist. They exist. And there are a lot of books where there is a lot of information about these kernels. For example, the well-known book by Levitan, Inverse Sturm-Liouville Problems, Marchenko, and so on. There are hundreds of books about this. So we, what we succeeded was to just to construct this kernel, in fact. So in this paper, joined with Luis Navarro and Sergei Torba of 2017, we proved that these kernels, for example, the kernel C of xt, they admit such a nice representation with the Legendre polynomials from the first talk of this conference. Okay, This is just Legendre polynomials. And the most important point here is that these coefficients Gn of x, they can be constructed. For example, if you solve a direct problem, so you know the potential Q, you just can construct this coefficient by a simple recurrent integration procedure, which looks like this. So you have some Cn of s, which are known, okay? And you integrate the previous one multiplied by this, and you obtain the next coefficient, okay? But for us, we don't need the formula for Cn of s here, even. We have them, okay? But we don't need it because we are interested in the inverse problem. And for the inverse problem, everything is simpler, in fact, here, okay? Why? Because we know that the very first coefficient in this representation, G0 of x, is just our solution, C, corresponding to the value of rho equal to 0, okay, minus 1. What does it mean? That in fact, if somehow it happens that we find out which is the very first coefficient G0, we recover Q directly, okay, from here. So we should construct just the very first coefficient, nothing else. And something similar, of course, is valid for the kernel corresponding to the solution S. Okay, we have another representation. Now, what happens if we just take these representations, series representations for the kernels, and put them into our transformation operators? So we just take this representation for the kernel C, put it here, okay? And what we should integrate? We should integrate the Legendre polynomials multiplied by the cosine function here. What we obtain? We obtain the spherical Bessel functions, very good functions, very well described. Everything is known about these spherical Bessel functions. They are introduced in this way. And something similar happens with the second solution. So we have our Neumann series of Bessel functions for the solution C of rho x and S of rho x. They have such a form, okay? And now, why they are so unique and so interesting? First of all, we have good convergence properties. So they, for example, for every fixed x, the series converge uniformly on any compact set of the complex plane of the variable rho. But most important is that the following two features. The first one, which I mentioned, that the very first coefficient is sufficient to recover Q. Why? Because you just recall that this C is a solution, okay? So Q is recovered just from this formula. It's sufficient to know G0 or S0. It is the same. You recover the potential immediately. So just the very first coefficient. And second, even probably more important feature is that, well, we consider this partial sum, for example, for the solution S. We just truncate the series here. And we obtain these kind of estimates where the right-hand side doesn't depend on the real part of rho. Okay, so this means the uniform convergence in any strip of this kind, okay, in the complex plane of the variable rho. So small rho, very large rho doesn't matter. This approximate solution approximates equally well our exact solutions. And it is something that you can see on a computer. So there are, of course, much more properties of this kind of series representations. which can be found in this recent book of mine and in our recent book with Alexei Karapetyan's. Here we still receive a lot of critics and comments from interested readers. So one of them here. And well, but more recently, we succeeded even to obtain another representation, but for a slightly nicer potentials. So this series representation is also a Neumann series of Bessel function representation, but it's not only gives us the uniform convergence in a strip, it works even better. It converges better for a larger row, okay, first. And second, to recover Q, you don't need even to differentiate, even once, okay? Q is recovered from just an algebraic combination of first coefficients of this representation. Look, for example, C of rho x has such a nice representation where, of course, cosine is always known, okay? And the first coefficient here, omega of x, is this integral of Q, is the primitive of Q, okay? Q minus and Q plus here, they are introduced in this way. So if somehow we find the first and the second coefficients of our representations, we recover Q from an algebraic combination of them without any differentiation. So it's even more attractive. And the convergence properties look like this. So the partial sums, they approximate even better our exact solution when rho grows, okay, when it becomes larger and larger. Okay, so, and now about the inverse coefficient problem. This is just to make you feel how, really how general is this inverse coefficient problem. This is this image just for this. So it's almost so general that, look, it's almost like think of a potential and we recover it. Okay, this is, this picture wants to say, think of a potential and we recover it. Okay, just I will now explain why is it. So I call it problem A here in this talk, and it looks like this. Imagine that, okay, we consider our Schrödinger equation. The potential is complex valued. It is from this Sobolev space. And Y, okay, we just have some solution for which we know its values at the origin for several rho k, okay? We know the derivatives at the origin of our solution for several rho k, and we know the values of this solution at the end point, at L, for the same values of rho k, okay? So from this data, from rho k, ak, bk, and lk, from this data, we should recover Q. Okay, this is the inverse coefficient problem, which of course has a lot of applications and so on. So just here, let us know that in terms of our solution C and S, this solution Y has such a form. Okay, this simple form, just to remember it. So why this problem is that general? First of all, the well-known problem and very important in implications, in fact, the recovery from a while function, it is a special case of this general inverse problem. So in this case, the while solution has such a form, so its derivative at 0 is 1, the solution at L is 0, and the while function is precisely the value of this while solution at 0. Okay, this is just a definition. So the problem consists in recovering the potential Q from the knowledge of this while function. So in our notations, we have that AK, they are just these values of M at the points rho k. BK is 1 because of this. Okay, this is our BK here. And LK are 0 because the values of our function are 0 at the end point. So this is a special case of our general problem. So the famous and classical inverse two-spectrum problem is also a special case. So just trust me from one of the previous talks. Okay, it's easy to see. And for example, the scattering problem on a finitely supported for a finitely supported potential is also a special case. What happens in this situation? So you have the potential Q, which is 0 up to 0. Then it is some complex valued function in general, Q of x, and then 0, okay, outside. So a plane wave, for example, this one, is incoming from minus infinity, interacts with the potential, and then the part of it is reflected, the part of it is transmitted. This is a classical problem, in fact. And the part which is reflected, so here the wave has such a form where R of rho is the reflection coefficient. The part transmitted is this transmission coefficient multiplied by the same plane wave. And so the resulting wave outside of the interval has such a form. So for negative x, it is this combination. For x greater than L, we have this solution. And so we can easily rewrite our problem in terms of AK, BK, and LK. So here AK will have such a form because they are values of our solution at 0. The derivative has such a form, and LK, they are these guys. Okay, just rewriting in our terms. So this is a special case of our general inverse coefficient problem. There are much more examples, just let me skip them here. So of course there are some methods which were developed for inverse Sturm-Liouville problems. So for example, these are just some references, but I would like to mention that all these methods are iterative. Our method is direct. None of these methods can solve problem A. None deals with complex potentials because it's just a very challenging problem, and the method which I'm presenting to you works equally well for real valued and complex valued potentials. And many of the methods introduced before, they need some additional information on the potential in order to begin. Okay, for example, the method from here, they need, for example, what is called the mean of the potential. This this integral of Q, which is you can't obtain from anywhere in applications, in fact. So our method consists of 2 steps, just very simple. And in both steps, we use the Neumann series of Bessel functions. So the first step, we immediately from the input data, we obtain the values of our solution, C of rho and S of rho, but at the end point. Okay, just both solutions at the end point of the interval. And then somehow we should convert this information into the information on the whole interval. And this is a very interesting problem. In fact, it arises in a lot of approaches, so it is behind of. And here we propose a new solution for this problem, which is based on a a very simple, just trivial observation, in fact. So let us consider a third solution for the same Schrödinger equation, which satisfies these initial conditions, but at the end point L. So we call this solution T of rho x. It is 0 at L, and its derivative is 1 at L. So it's like the solution S of rho x, but centered at L. Okay, let's say. So it's very easy to see that this solution T of rho x has such a nice representation in terms of S of rho x and C of rho x. So these are just these C and S evaluated at L multiplied by the corresponding function. It's very easy to see that this is so, and this is a generalization of this trigonometric identity, in fact, okay, which is the same equality for, but when Q is 0, okay? So we use this identity for our second step. So the method consists in the following. We take our input data and use NSBF to obtain C of rho L and S of rho L. And then, having them computed, we put them in this equality, and instead of T of rho x, S of rho x, and C of rho x, we use their Neumann series of Bessel functions representations here, from where we obtain directly Q of x. So how it works? Now, the first step, we substitute this Neumann series of Bessel functions representations in this formula. When Lk are known, they are the values of our solution at the end point, and we know that the solution has such a form. So here we substitute the NSB of the Neumann series of Bessel functions representations, and we arrive at some system of linear algebraic equations. So for the coefficients omega of L, Q minus of L, Q plus of L, and so on. And these guys are known, okay, from the input data. So from here we compute all these coefficients, including several of the coefficients from these series representations. So this is the first step. This gives us the possibility to obtain these partial sums of our solutions evaluated at L, and for which we have these nice convergence properties, okay, the uniform convergence in a strip, okay. And second step, we just do in fact the same thing. So these guys are known, and we put here the Neumann series of Bessel functions representations and derive immediately at another system of linear algebraic equations, where these are known, AK1, AK2, and so on. These coefficients are known, and what we are looking for is these unknown coefficients, omega of x, Q of x, which is introduced in this way, and so on, okay? And in fact, we just need to recover the very first two of them, omega of x and this Q capital of x. That's it. So, because finally the potential is recovered from an arithmetic combination of these two. So it's really very simple and more or less how it works. So what I'm showing to you, in fact, no other method can do something more or less similar, okay? I'm trying to explain why. First of all, a very general problem. So you just take any values rho k, you take your input data there. For example, AK, BK, you can define somehow. For example, sine of rho k, cosine of rho k. You know what are the values of your solution at the end point, and you recover Q. Look, here, for example, Q is complex valued, okay? So this is the real part, this is the imaginary part. The real part, if somebody did numerical computation, probably they know that just when your function changes, so grows, for example, rapidly, or have a very large range of the values, it's already difficult. So the real part, for example, here grows up to 1000, okay, in the interval from 0 to 1. And the imaginary part is oscillating. The maximum absolute error, which gives our method here, is of order 10 to minus 3, okay? Now, another example for a function, for example, which has discontinuous second derivative, because I'm working with the Sobolev space H1. So discontinuous second derivatives. So, for example, looks like this, and the maximum absolute error is of the same order, 10 to minus 3. Okay, this is more or less how it works in practice. And recently we implemented this method on quantum graphs, which are just you have your Schrödinger equation here on every interval and some compatibility conditions at the common vertices. Okay, so these are very important things, of course, and they are called quantum graphs since the discovery of graphene. Okay, before they were called networks of differential equations. Okay, but so of course they arise in many applications, and they are computationally they are really very challenging. Okay, to solve inverse coefficient problems on quantum graphs. In fact, practically there are no references. Okay, just I can give you probably one, in fact, reference where people tried to develop the method for inverse coefficient problems on quantum graphs. And so we managed to combine together with Sergei Avdonin from the University of Alaska and Kira Khmelnytskaya from the Autonomous University of Querétaro. We managed to combine the leaf peeling method, which invented Avdonin and Kurasov in 2008, which just allows to you, when you solve a problem on a sheaf, for example, this is a sheaf here, you can cut it out, okay, and continue. So you recalculate your spectral data on the smaller graph and continue the process of recovering the potentials on other sheaves and so on up to the end. So we managed to combine this leaf peeling with our approach on Neumann series of Bessel functions. And for example, this is an illustration from that paper where it was the while matrix was given, for example, at 180 points for a quantum graph which consisted of 18 edges. And so this leaf peeling procedure was necessary in this case, and this is more or less the result which was obtained. By the way, here this n was just 9, which in all the cases, which means that just with 9 terms in these partial sums, you obtain this very satisfactory accuracy in this case. So thank you very much for your attention.
Thank you very much for the very nice and interesting talk. Are there?
Did you try to use generating function for Legendre polynomials to relate with your series? And then also question about the Mellin technique, Mellin transform. To use representation for Bessel functions, try to use to represent solutions of your equation. I think it could be treated as a double Mellin transform, so related to gamma function series and so on. I think it's some idea what I'm trying.
The generating function here, well, we didn't need it, in fact.
Yeah, you write series with Legendre polynomials, and then it depends on t over x. So we try to make substitution and try to use generating function to relate with your coefficient. I don't know, I just thinking about this idea.
I don't know.
And also t over x, it's some Mellin convolution kernel, so can be Mellin type transforms could be used as well.
T over x is just because in general we work on an arbitrary interval. Okay? So in which sense? For example, we need it for a point x. So we need to obtain our series on the interval from 0 to x. Okay, this is why t over x is just technical stuff. And the Mellin transform, I looked.
Then you introduce, just put Heaviside function and then just extend on half axis and try to use Mellin transform. And because we have some images of Legendre polynomials with exponential functions, some Mellin transform, and play with gamma functions, I think.
You see, here, in fact, what is important is that these spherical Bessel functions, they are very nice, and they possess the orthogonality property from -infinity to infinity. This was the crucial point. In fact, apart from that, I don't know what more we can introduce here.
Okay, it's just my imagination. When I see Bessel function, I need to attack with this kind. Thank you. Yeah.
I see. Thank you.
Any other question or comment? Okay, so then let us thank the speaker again.
Thank you.